Okay, moving onward. Um, we have an equilibrium reaction here, the Haber process that we've already talked about. The industrial creation of ammonia is made from this reaction under a high heat and high pressure. And we have basically just a synthesis of ammonia. It just so happens that under these circumstances it's equilibrium. And what are they asking? At the start of the reaction, there are 0.249 moles of N2, 3.21 times 10 to the negative 2 moles H2, 6.42 times 10 to the negative 4 moles of NH3 in a 3.5 liter container at 200 degrees. If the equilibrium constant is K is 0.65, are we at equilibrium? Which way do we have to go to get to equilibrium? Okay, on this type of problem, they're giving us the concentrations of all species, and they're asking us if we're at equilibrium. Okay, what this problem is really asking is to solve for Q. Okay, Q being my NH3 on top here, the product over reactants. So NH3 stoichiometric ratio, square it, and that's concentration. Apologize, I don't have my tablet. The reactants on the bottom, and they are not squared because it's 1 for the nitrogen and hydrogen's not squared. It is indeed cubed, H2. Okay, and this is to the 3. Basically, we have our Q equation, which is real world data. Is it at equilibrium? Maybe it's got to go to the right, maybe it's got to go to the left. We don't know. How do we find out? Well, we have our Q expression. All we have to do is plug in all these values. Plug in all the values, solve for Q, and see what direction we actually have to go. Okay, so when we do that, it's just a plug and chug. You just insert our concentrations. Okay, they figured out each concentration by dividing each term by 3.5 liters. Is that my phone? Pause. All right, we're back. So they solved for each molarity by dividing by the volume. And you can see that all they did was they used that same expression that we created with the squared NH3 on top, the cubed H2 on the bottom, plugged all the values in, and solved for Q. Okay, now if you remember, the K was equal to 0.65. Our Q is equal to 0.611. So it is almost at equilibrium, but it's not at equilibrium. Okay, since it's smaller than K, what does that mean? Okay, that means that we have too much of the reactant. Okay, too much of the denominator. Right? When your denominator gets large, the unit gets smaller. When the numerator gets large, your number gets larger. So since we're too small, that means our reactants are too big, okay, compared to the equilibrium concentrations, which means that we must proceed, okay, towards the product, towards the NH3. Okay, I can already see that that's a little bit of a typo, NH3. In any event, though, we must go this way a small bit in order to achieve equilibrium. So the answer is no, it is not at equilibrium, and we must actually go to the right, to the product side, in order to achieve equilibrium. All right, we've already talked about this. 1 means perfect equilibrium, okay, as in the reaction is a tie ball game with a 50-50 mix. Anything greater than 10 for a K number, you're basically saying that the reaction goes basically to completion. Anything less than 0.1 for a K number means that the reaction barely does anything. Okay, this would be something along the lines of, it's not really a reaction, it's a process, but dissolving gasoline in water. Okay, it's an equilibrium process, but it barely goes forward. Okay, now we're actually going to start having a little bit of fun with algebra. Calculations of equilibrium concentrations. Okay, this is the most popular problem that we're going to encounter. Giving us a K value, giving us a starting concentration, having you find out equilibrium concentrations. This is where that ice box is really going to be very, very important for us. Okay. Here's our reaction here. H2 plus I2 yields HI. Stoichiometric ratio, it's 1:1:2. It's balanced. A mixture of 0.5 moles H2 and 0.5 moles I2 are placed in a 1 liter stainless steel flask at 430 degrees Celsius. Calculate the concentrations of all species at equilibrium. Okay, the equilibrium constant is 54.3. Okay. I'm just going to make a little bit of room here. Okay, so this is basically all the information that we actually need. Pull this down, get me a whiteboard. We have a K value, 54.3. What does that mean before we even start? We already know that we're basically not going to have any reactant left. Okay, since K is so large, this reaction is going to proceed very, very far to the right. Okay, so we already know that it's almost going to be completely HI in the end, but there will still always be some H2 and I2. How much? I don't know. We'll find out. Okay, I'm going to do my ice box. We have a 0.5 and a 0.5. And to be true with sig figs, we should really start putting the zeros in. And we start off with nothing for the HI. Okay, this is our initial. This is our change. We already know the direction. We're starting with reactant, nothing in the product side. So we know we're going to be losing or consuming. Wait, I put a 2 there. We're going to be losing or consuming reactants. So they're negative X. And we're going to be gaining product. So it's positive X. In this case, it's positive 2X. Okay? Because it's gaining, it's going to be positive. It's 2X because of the stoichiometric ratio. Equilibrium is always just adding up these two lines. Okay, it gets a little redundant. 0.5 minus X. 0.5 minus X. Tablet would be nice and handy right now. This one's 2X. We're actually almost done with this. We know that K equals 54.3, no unit, 54.3. Remember what that means? It means that it's an equilibrium, that's true, but it's almost entirely product-based. And that equals 2X. Okay? That represents the concentration of HI. 2X represents the concentration, but don't forget that it's also squared. Some of us have trouble with that. You start to think that, wait a second, I already used the stoichiometric ratio once. Why do I put the squaring in? Okay. You have to realize that the K expression is squared. Okay, the product in this case is squared. Yes, it comes from the stoichiometric ratio. Yes, the algebra of actually doing the concentrations also uses that same 2 to show that our concentrations will be 2X from whatever X is. Okay, it's all algebra based. It is a little redundant, and it is true that we're using the same 2 twice. All right. On the bottom we have our our H and our I concentration, and I'm actually going to consolidate these because they're both identical, and just call them squared. All right. Again, I apologize for being sloppy. I do not have my tablet with me, which of course is a lie. I have my tablet with me. I do not have the stylus to the tablet. All right. So our equilibrium concentrations are represented by our E here. These are what we have to actually solve for. Okay, but these are unknown concentrations. They can easily be solved if we knew what X was. So I guess the question of the day is solve for X. Now, if this was algebra class, I would expect this to be, take a few minutes to actually pull off. This would give you a little bit of a stress, okay, in order to actually solve for X. Luckily for us, we're in a position that we can rely on our actual calculator to handle this for us. Okay, what I mean by that is, what I'm going to do, all right, in my calculator, what I'm going to enter for my Y1 is going to be a negative 54.3. Basically, I'm going to solve this guy for 0. Okay, if I solve this for 0, I'm going to put the 54.3 on the other side by subtracting from both sides. Plus 4x squared divided by 0.50 minus x squared. It's the worst looking 0 ever. Okay. 4x squared, where'd I get that from? I just, instead of using extra parentheses, 2x squared is 4x squared. Okay, because the exponent is on the outside of the parentheses, you have to square both terms inside. So I just simplified that a little bit. So again, what I do, I solved the k expression for 0, which meant that I had to throw the 54.3 on one side. It's easier for me to show you how to pull this off, how to actually solve this in class, but I can easily solve this now and get a precise answer for X. Okay, when I get my precise answer for X, I can go ahead and solve my equilibrium concentrations. Okay, let's see what they actually did here. They're doing the same exact work that we did. Okay, looks familiar. 0.5 minus x, 0.5 minus x, 2x. And they solved for x as 0.393. They also did I do like the square rooting in order to make it a little simplistic, but they solved this the easier way. I solved it the harder way by using the y1 function, just because most of the times that's what we have to do. So they actually noticed that you could square root everything to simplify it and solve for x. Okay, so say they solved for x. You know what x is. So now to actually answer your question, the question they were asking, solve for the equilibrium concentrations, you would have to use the x value and plug it back into what we had for our E. Okay, so let's just do one of them. We know that the HI concentration is going to be 2x, which is now 0.393. They wanted the concentrations of all species. The HI is going to be 2 times 3.393. Okay. What's the concentrations of H2 and I2, respectively? Well, it's going to be the 0.5 minus the 0.393. Okay, and that would be actually for both of them. Okay, so you're going to have 0.500. 0.500 minus the 0.393. All right, what does that equal? That equals both the H2 concentration and the HI concentration. Okay, so now we actually solve for all species in equilibrium. And that's what they're asking for, so the problem is complete. Is that my phone? Is the phone ringing? Pause. All right, moving onward. You can see they did that math for us. Note that the answers can be plugged back in, and I highly recommend doing that if you actually had the time. It only takes 15 seconds to plug all these numbers back in. Okay, it's basically this number squared on top and then this number squared on the bottom. So you're just dividing those two numbers to make sure that you come back up with the K value. Only takes a second. Why not do that? Okay, now what about this question? For the same reaction, now we have different concentrations of H2HI, and they give us actually the HI concentration. Calculate the concentrations at equilibrium. Okay, equilibrium still is 54.3. Okay. Well, your first move on a problem like this is to find out if we are indeed at equilibrium or not. And specifically, I don't think I like the way they start just getting involved in doing it. Okay, I think in order to find out the direction of what this problem is going, you have to do a Q. Okay, so if you're doing a Q, you're going to plug in all these values. Basically, as I grab my calculator, you're going to take your HI concentration and square it, 0.0224 squared, divided by your two reactants, 0.00623, okay, divided by, again, 0.00414. And when you do that, you're going to find out that Q, okay, notice that it only took me a second to calculate Q. You're going to find out that Q is equal to 19.45. Okay, so Q is smaller than K. Right? When you compare the two, you're going to see that Q is smaller than K, which means that the denominator is too large, which means that the reaction is indeed going to go, we're not at equilibrium, it's got to go to the right. Okay, they're not doing that step in the PowerPoint, and I really should add that. Okay, they just jump to it and assume that that's what's going to happen. Okay, they actually assumed that it was going to go to the right. I don't know if I specifically like doing it that way. I think you have to basically do a Q in this case and don't assume anything that's going to go right or left. Why is it important to know which way it's going to go? Well, since we're going to the right, which is classically the case, we have the minus for our reactants plus for our product. We have to create more product, so it's going to get the positive. Okay, we're losing or we're consuming reactants, it gets the negatives. If Q was larger than K, the whole problem would be done exactly the same way, except I would have positives on this side and a negative on the product side. It makes sense. So I'm just going to be going the opposite direction, so the signs would flip. Note that we set everything up the exact same way as before. The numbers aren't clean anymore. What I mean by that is you can't just have a squared denominator. If you remember, we started with 0.500 minus x for both H2 and I2. Can't do that. We can't square the denominator because we have different values for both H and I. Okay. Now, since it's a little more complicated, I'm actually going to ignore this whole bottom aspect the way they solved it. I think that's much too time consuming. Now we're going to do it my way and take advantage of the calculator. Okay. As soon as we get, solving for 0, as soon as we get back into class on our next class period, we're going to be able to solve this on our calculator in about 20 seconds. And when we do it on our calculator, it's going to be 100% correct. Doing the heavy algebra is also a proper, totally mathematically acceptable format. The problem with doing the algebra is it won't take 20 seconds. And the problem with the algebra is that you're more inclined to make mistakes. Okay, the College Board allows us to use our calculators to solve these complex algebraic problems solving for x. So we're going to do that. Okay, solving for x. X is, in this case, they're doing the whole quadratic and everything else. X is, in this case, 0.00156. The answer to the question, what are the equilibrium concentrations? All you have to do is just take your initial, okay, and plug in the x to figure out what the final concentration is. So once you know that x is 0.00156, you can easily figure out by plugging in your x value what the equilibrium concentrations are for each species. That's what they're asking for. Okay. I can't stress this enough. The ice boxes get a bad reputation. Typically, I really enjoy them, and we usually do really, really well on these. Okay, and we're not going to talk. We're actually done for the whole math of equilibrium for now. Okay, now we're back into conceptual. Just cover a couple more concepts. All we have to do is just practice our equilibrium stuff. Okay, and then move onward to acid-base equilibrium, which will be very similar to this equilibrium. Love the word. Gentleman's last name, Le Chatelier. Okay, Le Chatelier's principle is that if a stress is applied to a system in equilibrium, the equilibrium will shift to relieve the stress. Okay, now what they mean by this word stress is altering the reaction in any way. Okay, you could change the temperature, could change the pressure, you could add a component, add a concentration, take concentration away, things of that nature. Okay, and what I mean by this is that, first of all, this should be a double arrow. Not really liking this. Okay, so there's my equilibrium. If I add C to this, if I have equilibrium established and I add C, equilibrium means I have all species occurring and they settled down, right? The reaction slowed down, went to a halt where the rates going forward and reverse are the same. But if I add C, and I just picked one of them, let's just pick C. If I add C to the container, then equilibrium will actually shift to relieve the stress of the added C, and it will switch towards the reactant side. Okay, this should make perfect sense when you're thinking back in terms of Q. If I add C, it's almost like you have to do a Q equation on it really quick in your head. Not numbers based, but more theory, math theory. If I add C in that Q equation, I make the numerator larger, which meant that Q was larger than K. Q larger than K meant that we had to shift towards the reactant side. Okay, so once you understand Le Chatelier's, you don't have to go back and start thinking of Q equations, but that's actually how it works. And the same goes if I take C away. If I take C away, the reaction will proceed forward to make more C. Okay, so that stress would be taking away C, and the reaction would respond to make more C. I could take all of my C away, and the AB would start reacting and make more C until equilibrium is established again. Alright, so adding a substance would make the equilibrium shift to consume the added substance. Removing a substance means the system would shift to add more of the removed substance. Just what I just talked about with C. The same thing with volume. Okay, if these are both gases, okay, I have my gas making two gases. If I reduce, this is an equilibrium reaction. Let's say it's done in a piston. Okay, what I mean by that is it's done in a system like this. Okay, there's my piston, or my cylinder, I'm sorry. Here's the piston. Moves up and down. It's hooked up to some sort of motor that can move this thing up and down. So if I push this down, this volume gets smaller. If I pull this plunger up, the volume will get larger. This is my volume. Okay, if this reaction is done in the enclosed container, okay, where my V is, then what would happen if I reduce the volume? That's my stress. Reducing the volume means that I'm going to push down on the handle here and reduce my V. If I reduce the volume, okay, volume goes down. If volume goes down, what happens to the reaction? Which way will the reaction go? Well, if I reduce the volume, that means pressure goes up. And if I reduce the volume, pressure goes up, the reaction will shift to less gas. This one's the hardest one to see. If I compress it, it's actually going to go to the reactant side because it's almost like a pressure relief valve. The reaction can react in order to make less pressure. Okay, I'm reducing the volume, which adds pressure, and the equilibrium equation here will shift to the reactant side to compensate for that, to make less pressure. And what I mean by that is I have 2 moles of gas on this side and only 1 mole on this side. So when the reaction proceeds to the reactant side, okay, when the reaction proceeds to the reactant side, I make less gas. My gas can be cut in half if it went totally to the reactant side. It's not going to go that far. But I'm just, my stress is adding pressure, so it's going to go to make less pressure. Okay, Le Chatelier's principle for gases, pressure-wise. Okay, in this case, changing pressure, which is the same as changing volume, they're all gases, but it's 2 to 2. So it actually doesn't do anything in this case. Temperature plays a role. Okay, the K value we said in class, the K value does change with temperature. But temperature can also play a role on pushing the reaction back and forth. And that's because our reaction could be endo or exothermic. Okay. endo or exothermic. If it's endothermic, what does that mean? Well, if it's endothermic, it means that it requires heat to react. It means that heat is a reactant, not a product. So A plus heat yields B, equilibrium yields. Okay, and that's supposed to be an H. If it's endothermic and I add heat, then the products will get larger. I'm doing a shift to the right. If it's endothermic and I remove heat, then I will shift, okay, to the reactant side to make more heat. Okay, so temperature can play a role in this as well. And in class I said that temperature can play a role because of the way the reactants and products react. That was perfectly acceptable. The endothermic and the exothermic would probably be, which is the same thing, but maybe would make more sense if I were to use that demonstration to explain it. So in this case, going forward is endothermic, going backwards is exothermic. So I can speed up or slow this reaction down by adding or removing heat. Okay, so in this case, endothermics plus heat shift to the right. Okay, so this is exactly what I just said. I said I had A and B for reactants and products. Exothermic means the heat's over here. Okay, so adding heat would mean you would have to shift it towards the reactant side. All right, so it's the same thing. You know, when you're adding heat as a reactant or a product, then it's the same thing as adding or subtracting reactants and products. All right, so in summation, we have the Haber process here, which is a exothermic reaction, which means it's plus heat. If I add N2, I make more product. I add product, I get less product. It means it shifts back the other way. If I add pressure, I get more product. Remember, we said that this was done at high pressure. Okay, if I add temperature, you get less product. Okay, but you had to do this one at high temperature, but there is a threshold there where temperature doesn't speed it up. It's a requirement, but it doesn't speed it up. It makes it slower. It goes towards the reactant side. And the reason why you had to do this at high temperature is because when you do it at high pressure, there's a Charles law factor there. High pressure means high temperature. Okay, so that's Le Chatelier's. Again, why do you get more product from high pressure? Because you have 4 moles of gas versus 2 moles. When you add pressure, when you compress it via maybe a piston, then the reaction will shift to make less moles of gas. So you'll actually make more product. Okay, consider the following equilibrium systems and predict the direction of reaction by a change in pressure or change in volume, which are the same thing, on the system. In this case, I have 3 moles of gas versus 2. So if I add pressure, it goes forward. In this case, it's 1 mole of gas versus 2 moles of gas. So if I add pressure, it comes backwards. That's Le Chatelier's. Okay, same thing here. If I heat this one up, because it's endothermic, what does that mean? It means that the plus heat is on the reactant side. So if I add heat, it goes faster. It goes, I shouldn't say faster, it goes more towards the products. If I remove gas, it also goes more towards the products. All right, catalysts actually don't do anything to the equilibrium. A catalyst makes a reaction go faster, but in the case of equilibrium, it makes it go faster both ways. Okay, so in some cases it's needed because it makes equilibrium establish faster. Okay, so it's a positive attribute. but it doesn't actually make one side favored more or less. Okay, it doesn't change the actual K value. So effects of a catalyst and Le Chatelier's doesn't, there's no relationship. Okay, lastly, this is supposed to be a delta H. I have this reaction of making or creating ozone. And I don't know, I'm going to have to actually make up what these boxes are. So let's do that. This was delta H. Okay, meaning it's endothermic. Okay, so the plus heat was on this side. It's a reactant. What effect is raising the pressure? Well, if the pressure goes up, because it's a 3-to-2 ratio, it means it's going to go towards the products. What if I increase the volume? Second scenario. If I increase the volume, that means pressure goes down. It's going to go towards the reactants. What happens if I add more more O2 rather? If I add more O2, I'm going to go towards the products. I'm going to consume the O2. If I decrease the temperature, it's going to go backwards and create more temperature, create more heat. So it's going to go towards the reactant side. What happens if I add a catalyst? If I add a catalyst, nothing occurs. Okay, so that's Le Chatelier's. They're usually multiple choice questions. They're actually usually very, very, very simple questions indeed.